I
Yeah,
believe this is a session for week 7 experiment, right? Yes lab.
week 6, I think.
Sorry,
This
yeah,
is
week 6. Week 6.
so. This is a doubt section. So we will start maybe in 2 minutes. We'll wait for everyone. I think everyone has joined. Okay, fine. Then we can
Sure.
start the
Yeah,
session. So,
sure.
uh, say one by one what all doubts you have.
Sure, ma'am. We can wait. Yeah.
So we shall start. Maybe we can start asking about the doubts. What all doubts you have. Yes. Venkat Subhash.
Yes, ma'am. Am I audible?
Yeah, yeah, yeah.
Yeah. Good evening, ma'am. Actually, I would like to ask, in my case, in the BJT characteristic experiment,
Hmm.
I'm able to get the characteristic if and only if I use an high resistance at the base. Instead of 1 kilo ohm, if I use 100 kilo ohm or 400 kilo ohm, something higher than 100 kilo ohm, I'm getting the result.
No. See, the base resistance RB is given so that to limit the current. Okay.
Madam, can you be a little louder, ma'am?
Yeah. Hello.
Yeah, ma'am.
So you are talking about the figure one, right?
Yeah.
So figure one, have you tried with RB is 5 kilo ohm, right?
No, no, ma'am. Actually, yeah, 5 kilo ohm. Yeah.
5 kilo ohm. So for 5 kilo ohm, did you take see the characteristic?
Yes, ma'am. What is happening when we are using 5 kilo ohm is we are getting a high currents instead of microamperes. We are getting some. I mean, why we are because we are using the potentiometer and precise control over voltage is not. I mean, we are not having a precise control over the voltage.
No, no. Because of the potentiometer, you will have a precise control. No, so potentiometer is 1 kilo ohm. So that 1 kilo ohm, you are connecting the RB to the variable end, right?
Yeah,
Correct.
yeah,
So 2.5 is connected to RB and you are connecting the RB to the variable end. So the voltage across the variable end and the ground will be the that we see that is what is the voltage applied to the
yes, ma'am. For the base.
BJT, right? Right.
Yeah, yeah,
So depending on that voltage, you can change.
yeah, ma'am. Then we should not use some high voltage, high resistances because using that we can get a good control over the current.
Yeah, yeah, yeah. So that is what this potentiometer is all about. So you can change the voltage. No, you can lower down the voltage by changing the RP value, right?
Yes, ma'am. But the thing what is happening is we need
Uh,
to, even though if you are giving an voltage of 0.8, because the resistance is not too small, but it's small when compared to 100 kilo ohms, very easily the BJT is going into saturation region.
is it so? How much resistance you are giving in the RP? RP you have calculated open RP, open circuit RP. You have
So,
calculated when maybe high voltage you are giving RP as 5 kilo ohm as given as in the uh, means, in
so
the
the
manual.
V1. Hmm.
So you have to remove the RB means remove the short circuit open circuit the RB.
Okay.
Okay, then take the value across that variable end and the ground. You will get the open circuit value of that RP value, potentiometer value, right? How much voltage. So if it is at a half, then 2.5 divided by it will be what 1.5 volt will be across RP, right?
Yes, ma'am. Ma'am, actually,
Ah.
in order to get 10 milliamperes of, sorry, microamperes of current, we need with this particular 5 kilo ohms, then we have to maintain VB as 0.65 because VBE is 0.6 in our case.
VB is 0.6 here.
Yeah.
0.6. Okay, fine. Huh.
So
VB is
to get
0.6.
10 microamperes of current, the voltage across the resistor should be around 0.5
Across the register. Which register?
base resistor.
RB should be around 10 microamp, right? Just a minute.
10 microamperes. So it should be 0.5 volts.
Yeah, 0.5 volts. Correct, correct, correct.
Yeah,
Yes.
even though, I mean, if there is a slight variation, it's a, I mean, very easily it's going into saturation.
See, this transistor we cannot, we are not able to do the experiment in for BJT because we don't have the same model as you are given in our lab.
Yeah, the
So,
solution which we are, I mean, what I found, at least in my case, working was I am using 400 kilo ohm. Even with 100 kilo ohm, it's working fine, man.
100 kilo.
If,
But
if you use 100
it
kilo
is
ohm,
very
then we
high, right?
can, yeah, it's very high, but we can increase the voltage from until 1 volt.
So
Then it
10,
won't be an issue.
we need 10 microamps divided by 100, right?
Yeah.
Into 100 kilo.
Yeah.
So 10 into 10, 6, and here 10. So it will be how much voltage across? So you are saying,
We could give around 7 or 8 volts, then it will work.
but if you keep 5 kilo ohm and RP value is how much you are keeping RP value at the time.
In my case, ma'am.
In my case, how much voltage you are keeping across RP?
Okay,
So,
okay. Across the RB, actually, I'm using 400 kilo ohm resistance, so that even though I give 2 volts, it's not an issue. I'm getting an very less current of tens of microamperes. So using that, I mean,
maybe
for the
check
sake
with
of compare.
how much like less you can go 10 5 kilo ohm,
Okay,
about
okay. I have to
huh,
decrease by a factor of 5 from 100 kilo ohm.
maybe 50 kilo ohm you check how much
Okay.
is it coming,
Yeah, I'll check it.
and then you can get a solution through it
Ma'am,
because
actually,
we
what's the issue? Because I mean, the main agenda is only to control the current, right? There's
yes,
no other.
correct, correct, correct,
So
correct.
whatever resistance we use, it won't. I mean, it
No,
won't
yeah,
matter, right?
correct, correct, correct. I agree. Because whatever the IB, that over that the IC value will change,
Yeah,
and that is what you just need to see the transistor characteristics, right?
yeah,
So that is what is the aim
yeah.
actually. But the RB value is so much high. I will check once, like and talk to the professor once about it,
Hmm.
because we are not able to experiment it in our lab because we don't have that transistor
Yeah, it
model
is a metal
with us.
can.
Yeah,
Metal can
so
do
that is
flash.
what one problem. But I'll make a note about it.
Yes, ma'am. Yes, ma'am.
Okay, so RB value you are keeping it as 100 kilo ohm also it is working fine,
Yes,
right?
ma'am. It's working fine.
Right.
I
Okay,
mean,
and at that time you kindly check what is the RP value you have kept, so that we'll
okay,
know that
VB,
how
yeah.
much RP means
RB is
the
100 kilo ohm.
no, not RP. I'm talking about the potentiometer.
Okay.
So, what is the voltage across the variable end and the ground? What is the voltage across that point? You
Yes,
check
ma'am. I'll
please
check it.
once.
Yes, ma'am. I'll check it. And actually, it is around 0.8, I guess. But once again, I'll check it and I'll let you know.
You check this so that we'll get to know that how much
Yes, ma'am.
current is flowing through that.
Yes, ma'am. Actually, this thing I have calculated, ma'am. In my
Hmm.
case, around 20 microamperes is flowing.
20 microamperes is fine.
Yeah. Yeah, because some few tens of microamperes is fine, right? For
Yeah,
this particular beta.
yeah, correct, correct. So I will check once with the professor about it.
Okay, ma'am.
Yeah.
Anyways, if there is no reply from your end, I mean, today is the deadline. We can use
Yeah, you can upload
any
it.
high,
Yeah, yeah.
any
So
high
may I get your name, please?
mail ID, ma'am.
No, so you're Venkat Subhash, right?
Yes, ma'am. Name. Yes, ma'am.
Okay. Any other confusion?
Yes, ma'am. One more thing with MOSFET.
Yeah.
What is this threshold voltage of this MOSFET, ma'am? Because
Hmm.
I mean, in my case, I am getting a threshold voltage of 3.2 volts.
3.2 volts. Okay.
It's too much.
See, I checked. Yeah, yeah. Threshold voltage may vary. I have also conducted this experiment. A MOSFET I have conducted, not with the same model that you have been given,
Mm-hmm.
but we are having one MOSFET. So that with that I just checked the first experiment. Okay, that the transfer characteristics.
Mm-hmm.
Yeah. So the threshold voltage may be depending on the value. It can vary. Okay.
Yes,
Only
ma'am.
thing is that you should get a curve of the ID versus VDS that
Mm-hmm.
you have to show, right?
Yes, ma'am.
So such that the current should at some point the current is getting constant, right?
Yes, ma'am. It's getting constant. I
Constant,
mean,
but
at
very
very
small
low
range.
voltages. Yeah.
Very small range from so you're varying from 0 to 5 volt, right?
Yeah.
So maybe a very small range from 0 to that means
Yes, ma'am.
I think
Till
1 or 1.5. I think it will change, and then it
no,
will.
here
How much?
in my case, because the threshold is 3 volts, from
Hmm,
3.5 there onwards, it's constant.
1.5. See, threshold is you are talking about that is VT, right? VT
Yeah,
of
ma'am.
that MOS transistor, right? You are giving threshold means VGS. How much voltage you are giving, right? You are,
Yeah.
your threshold is which threshold you are talking about? Of
Okay.
which
So in my
which
case,
voltage?
what I have said done was the gate voltage I have set it to 3.2.
Gate voltage. Okay.
Yeah, I mean
How
before
how
3
do you
point,
how did you get voltage 3.2?
I have given 5 volts instead of 2.5.
So try with 2.5 volts.
No, ma'am, I am not getting any significant currents. I am getting everything in microamperes. I have tried at the maximum possibilities
So
with 2.5.
microamperes. See, first you check for 5 volts. Okay.
The
See,
gate voltage.
no, no, not gate voltage. I'm saying about, let's say 2.5 you connect.
Okay, for the
Okay.
gate.
For the gate through
Okay.
the potentiometer. Okay.
Mm-hmm.
Then connect the RP value, whatever. I have used 200 ohms that already given. Okay.
Yeah.
200 watt. Sorry. Says 200. Just a minute. Okay, just a minute.
Yes.
So you are connecting 2.5 volts and your RP of connected. Okay, then this RB is there. Okay, yeah. What I was saying, put your voltage at 5 volt first of
One
all.
second.
VCC.
I'm doing along. 1 second.
I'm also checking. Let's see.
So from the potentiometer, we need not to give any resistance right now because it may not matter much.
No, no, no. For BGT, yeah, yeah. For this
Awesome.
MOSFET, yeah, MOSFET, it is like that. Yes, correct.
Okay.
But you can provide RCs, RB as given R. You can provide this thing. Maybe you try to keep it RB, no problem. But it doesn't matter though.
Ma'am,
That
for the drain, sorry. Yeah, for the drain resistance, I'm keeping 1 kilo ohm.
1 kilo ohm that you have kept, that is RC.
Yeah,
RC you have kept, but it, okay, you can keep it. Just a minute, and let's check.
I mean, if we keep 1 kilo ohm, it's easier for calculations to things.
Hmm. Just a minute. But what you can do
Hmm.
is maybe fix the voltage of VCC
Okay.
at 5 volts first. Okay,
Okay. 1 second.
got it, right?
Yeah, got it. So what is the drain resistance? I'm using 1 kilo ohm. Is it fine?
1 kilo ohm, right?
Yeah.
Yeah, you can keep it 1 kilo ohm. That is not an issue.
Yes, ma'am, done. So VCC, I'm setting it for 5 volts for now.
5 volts for now. Maybe 1 kilo ohm you have kept it. Okay, fine. Then your DTH, see that how much, like if you keep the RP value, means RB at half, RP at variable at half of it. Okay, maybe
Okay.
500 and 500. It is 1 kilo ohm pot, right?
Yeah, ma'am.
So 500 and 500, that means 1.5 volt it should come, right?
1.25
25,
volts.
25
Yeah.
volts, right?
Yeah.
Now increase that value. Okay.
Okay. Wait, ma'am, I'm checking the currents.
So have you done that?
Yes, ma'am. 1 second. My whole software is lagging a bit.
Okay, no problem. I'm just telling what you can do.
Processor. Yeah.
Just the procedure, so that, so keep your 5 volt VCC at 5 volt.
Okay.
And then 2.5 you can you have connected through the RP, right? And RB is there, let's say. Okay,
Yeah.
according to the diagram that
Yeah.
is
Yeah.
there. So uh, you can vary the RP variable positions, right? Variable connect position,
Mm-hmm.
and change the voltage across the that across how much voltage is going through the gate, correct?
Yeah, ma'am. Yeah.
So for that you will get some voltage. Okay,
Yeah.
so you check that, then you get some voltage, no, then uh, across RC you connect your multimeter. Okay,
Okay. Across arts. Yeah.
RC, because it
Mm-hmm.
is said no, you have to connect across this how much ID is flowing, correct? In the MOS ID, that is the drain current, right?
Mm-hmm.
So you can connect a multimeter across RC.
Mm.
So you will, from there you will get a voltage across RC, right?
Yes, ma'am.
So that voltage divided the RC value will give you the ID value, right?
Mm-hmm.
So that you have you will get the voltage across RC, and now you change the voltage across voltage of VCC, that is a 5 volt. You make it little less, so you will get a constant value,
Yeah.
correct?
Yes,
So
ma'am.
now when you reduce, there will be a point that will the change is more significant, right?
Uh, yes, ma'am. Right now, I'm giving around 1.25 volts to my gate.
Gate, yes, yes.
1.25. Yes, exactly. I have given 1.25.
Okay.
And the voltage across my this particular drain
Maybe
resistance.
see VGS may be very, very high for your MOSFET.
Yes,
It
ma'am.
is
That's what. Instead of 2.5 volts, if I am giving around 3 volts, then it's working.
okay. Okay, I'll check with this. I'll also check.
And one of my friend, the same MOSFET, he is getting around 4.2.
Yes, ma'am. Mine is 3.7 around.
Ma'am, at least how to find that this is coming into saturation region?
Saturation reason you will find it out when that you are acquiring the voltage across RC, right?
Yeah, RC, yeah.
RC, right? So when you change that VCC,
Uh,
from 5 volt maybe 4.5 4 you change it like that.
Ah.
So the voltage across RC will be almost constant, almost not same but
Okay.
same in the same
Very
range.
little
Okay.
difference.
Very little difference. That's why ID will be also different, very same. ID also is almost same, right?
Yeah.
Correct.
Yeah. That means that
So
ID is constant.
ID is constant. So that is what. Now when you decrease, come close to 0.5, 0 come close to maybe from 1.5, then 1, then 0.5. At that area, maybe you can get a change will be more significant. Correct. So that area is you came out of saturation. Okay.
Okay, ma'am. Then here the thing is when I am decreasing from 5 volts to 4 volts, there is only like 2 millivolt. I mean 2 millivolt difference.
Very less. Correct.
Yeah.
Yes, it will be. That means it is still in the saturation region.
Okay.
Then you get it down to 2 volts maybe. VCC you give 2 volts.
VCC 2 volts. Okay.
Yeah, give 2 volts.
2 volts.
Because your VGS also is high, right?
Yeah,
so you
VG
cannot
is
get
around
down,
3.4 4 volts.
so you cannot get down before that. I think one formula is that VGS
Yeah.
minus VT should be greater than something. I think the VD. I think.
Yeah.
So that formula also you have to put into that. That should not go down lower than that. Okay.
Okay, then shall I lower the gate voltage?
Maybe no. You make it down to 2. VCC you can make it down to 2 volt.
But my gate voltage is only 3 point.
Okay, we'll check once. What is it? Whether it is shifting more, voltage is small, is there or anything still in the same domain?
Yeah, it's in the same position, ma'am. Even though if I make it 2 volts, it's in the same position. Almost a little change, not much.
How much is it?
I mean, very little change, not a much difference.
See,
Yeah, at 5 volts, the VC across this drain resistance is 150. At 2 volts, it's 140 millivolts.
I could not follow you. Can you repeat?
Yes, ma'am. Right now, my gate voltage is 3.4.
3.4. Okay.
Yeah, when the VCC is 5 volts, the voltage across this drain resistor is 150 millivolts.
150
Even though if I
millivolts.
decrease it down to 2 volts, the drain, the VCC.
So RC is you have kept 1K, right?
Yeah, 1K.
150 divided by 1K.
That means 150 microamperes.
150 microamps, right?
Yeah.
Now, when you decrease it down by 0.5 like that,
Even though if I come to 2 volts, the VCC, if I make it 2 volts, I'm still getting 140 microamperes.
140 microamperes.
Yeah, only 10 microamperes decrease.
No, it should not be like that. Just check. Checked it, but maybe I go. Just a minute, give me a second. Have you checked with 2.5 volts? Giving 2.5
When
volts?
it's 2.5 volts, I'm not getting any current.
Any current through that RC value?
No current. I mean, the voltage is only 0.2 millivolts across that resistance.
0.2
millivolts across that drain resistance. That means no current.
at what voltage?
2.5 volts.
No. 2.5 volts you are giving VGS, right?
Yeah, ma'am.
And what are you giving at
VCC, it's 5 volts.
5 volts you are giving. So voltage across RC, what you
0.2 millivolts. Millivolts. Yeah, you could easily neglect that one. It's very less.
Yeah, just a minute.
I'm not sure if I'm the only one facing the issue.
I am also facing the same issue.
Oh. Even in the data sheet, ma'am, the threshold voltage they have given as it may vary from 2 to 4 volts.
Yeah.
It is not clear.
Yes, ma'am.
Correct. It can very like that. So VGS can be high, no problem. But are you getting the curve like that? Like once it gets saturated, and at some point it is increasing from 0 to
So
something.
when we are having the gate, I mean VGS as 3.4 something, I'm getting a nice curve.
You're
Yeah,
getting a
same
nice
here.
curve.
Yeah,
Can
ma'am.
you show me the curve?
Ma'am, I haven't plotted it.
Okay.
I mean, I just got the intuition by seeing the values.
So you can you explain me what did you get if you're giving 3.5?
Okay, ma'am. Right now, let me just do it
Huh,
and tell you the values.
tell me.
Okay, now the gate source voltage is 3.4,
Okay.
and the VCC.
That is across the voltage across coming RP.
No, no, ma'am. Across RB.
RP, not RB. That is a potentiometer variable end and the ground. How much
Yes, ma'am.
voltage
Yes,
are
ma'am.
you
That's
sending?
what. That's the voltage I'm saying. Across
Okay.
the potentiometer variable. I mean the output of the potentiometer, right?
Correct. Output of the potentiometer.
Yeah,
How
it
much
is
is
3.4 exactly right now.
okay?
And now the VCC is 5 volts.
This is 5 volts. Okay.
The drain current is 143 microamperes.
140
3
microamperes.
143
143
microamperes.
microamperes. Okay, fine.
Now I'm
Now,
decreasing it to 4.5,
okay.
the VCC. And now the current is 143 microamperes. Coming to 4 volts, it is 142 microamperes. Coming to 3.5. Ma'am, are you making note of them?
Yeah.
Yeah, at 3.5 it is 142, same. No decrease in the current.
Then
And at 3 volts it is 141 microamperes. 2.5, 140 microamperes.
140. Correct.
And at 2
Same
volts
range.
it is 138.
Okay.
1.5 it is
Correct.
even at 1.5 it is 138.
Okay.
At 1
Then
volt it's 135.
1.5. It is
138.
138. Okay.
At
At
1
2
volt
also.
also it is 135 microamperes.
Okay, 135 and then
0.5. Even here I'm getting 130 microamperes.
130, right?
Yeah, it's
And at 0.25 you see.
okay. Here it is 120 microamperes.
0.25 it is 120.
I mean,
Correct.
it's not decreasing much.
But that will be like this only it will come, no? Here, see, in the 4.5 area, 4.2, 2.5 area, the change is very less. 1
Yeah,
microampere like that.
yeah.
And then it is changing.
Yeah, it is changing.
Correct?
Yeah,
So that it is changing more.
yeah, ma'am. If I
Maybe,
decrease the gate voltage by very less, even though
huh,
if you say 0.2 or 0.3, the
hmm,
current is literally dropping to zero.
okay. If you decrease the value from 0.
Now, right now it's 3.4 right gate voltage. If I decrease to
Huh,
3.3 at VCC is equals to 5 volts,
huh,
I'm getting the current as 40 microamperes. I
okay.
mean, it's getting
Okay.
dropped very.
But maybe you 40 microamperes you're getting, right?
Yeah,
So you change it again, like maybe 4.5, 3.5,
yeah. Let me
like
check
that.
it 2.5 once just.
Correct.
Yeah, 2.5 was it is 38 microamperes, very less decrement.
At 2.5, then at 1.5,
1.5 it is 37.
37.
At 1 volt it is same 37. Well, maybe should I decrease the volt resistor at the drain? Sorry.
Yeah, that is RC value, no?
Yeah, RC.
So RC, what it will be? The voltage across it will be reduced, right?
Okay, there's no much difference
Yeah.
because
So
current
it's
is
a
the only.
voltage. Current is dependent on the how much gate voltage we are giving, right?
Yeah. So it won't make change.
Change. Correct. So that is what the channel is found. That is one thing. Okay.
Uh,
Can you Can you see how yeah, this is constant discriminant. But try to plot the data of the previous one and
Yeah.
see how it is.
Yeah.
Yeah.
Yes,
Okay.
ma'am. Well, right.
Then plot the data and just get back. Okay.
Oh, yes, ma'am.
Yeah. So for others, what any confusion?
Ma'am, same issue as Venkata have.
Okay.
The MOSFET value is not as accurate as we mentioned in the data sheet.
Any other issue you have?
No, not right now.
You understood the last part of the experiment, right?
Yes,
Last
ma'am.
part 4. See, I'll go through it once. So part 4, you understood, right? What the optimum value you have to understand so that the LDR is there. It's the LED lights up. Correct.
Can you explain this part a bit, ma'am?
Yeah, I
Yeah,
thought
ma'am.
it might create some confusion, so that's why. So here, what you'll do, you'll connect the potentiometer, okay, for variable end of the potentiometer to the LDR. So the voltage across. So this there will be one voltage. I'll just share my screen. Are you able to see?
Yes, ma'am.
Yeah. So you are connected through a potentiometer to the LDR, right? Okay. So first of all, you will cover the LDR. So the LDR will have a higher resistance, right? When it is dark, right?
Yes, ma'am.
Yeah.
When it's dark, it will be having lower resistance.
Is it
No. Higher resistance.
I
Yes, ma'am.
guess
correct? Correct.
You are
no,
right.
Yeah.
no. Yeah.
Yes, ma'am. You are right.
That's what. Yeah. This it is with when we expose to light, the resistance decreases. The curve is exponential decrease, right? So I think that is the curve. Maybe please confirm. Higher resistance only. That is what I have seen. So you will cover the LDR and check and change the RP value. Okay, you can follow.
Yes, ma'am.
Yeah. So change the RP value and accordingly the IB will change. No. So you check the value where means take the value where the LED will light up. Okay. Now,
Okay.
when you remove your hand and when the LDR is exposed to the light, the LED, the voltage, the resistance of the LDR goes down. Okay, so the voltage across the LDR also goes down. So the IV will decrease. So accordingly, the IC also across the that LED will decrease. So LED will maybe switch off. Okay. So confirm that experiment once. Okay. That is experiment. Okay. So that's why it is told that try to find the optimal position of the variable series resistor. Okay. So you have to change the resistance value, pot value, and find the position where the LDR lights up. Okay.
Yes, ma'am. In this experiment, what I have observed was using the potentiometer, we are able to adjust the brightness of the LED, and using the
Yes.
LDR, using the outside light, we can adjust it using the LDR.
I didn't get using the LDR.
I mean, using the potentiometer, we can set a like
Yeah,
reference brightness.
and then if you
Using LDR, you can just try switching it off. I mean, turning it off and on. That's it.
correct.
Yeah.
So that thing you have to find it out. Or another way is that finding out, check that if you are exposing the LDR to high light, low light, like how it is, whether it is affecting the LED brightness or not. Okay.
Yes, ma'am. It is affecting.
Yeah, so that is what you have to, because when you are exposing to highlight, like the resistance goes down, and if you're increasing the darkness, so the resistance goes up. So accordingly, the brightness also should change. So that is what is the objective of this experiment. Okay. So this is so you have plotted the value for most.
Do we need to record any values of that
It is
RB
showed, right?
voltage or something?
Yeah, yeah, yeah. Oh, which part you are saying?
Part 4 only.
Part 4. I just checked. Note the voltage across the
Voltage across LDR.
and the current through the LED when the LDR is exposed to the light and kept in darkness.
Okay.
So you can take voltage across RC, that will give the current through the LED, right?
Okay, ma'am.
Did you follow?
Yes, ma'am.
Understood? Yeah. So and the voltage across the LDR, you have to take it like this, okay? Across LDR, for which the LED means a different, not the voltage across the LDR and the is exposed to light and kept in darkness, okay?
Okay, ma'am.
You have to show in the video that this is the voltage across. If it is in dark, that this is the voltage across the LED, because sometimes you just infer the explanation and you don't show me the value, so this is difficult to verify. So you need to show me the video, okay? Anything else?
So, ma'am, in part 4, what we
Yeah.
have to do is we have to make 2 observations in both the cases. One is when the LDR is covered, we have to
Yes.
note down the voltage across LDR and the voltage IC. We have to note down the current in the IC.
Current in the LED. So that will be the drain current, right?
Yeah.
ID. So
Yeah.
that you can measure by measuring the voltage across the RC and then dividing the value with the RC, right? That will give you the ID value, correct?
Yeah. So 2 observations
That you
in
have
2
to,
cases.
yeah.
In 2 cases.
And you have to give an explanation how the LDR, when it is exposed to darkness and light, how it is changing the brightness of the, whether it is, the brightness is changing or not. Okay, after fixing the optimized RP value.
Okay. Okay.
You understood, right? First of all, you will keep the LDR in dark and you will optimize the RP value for which the LED is getting on.
Okay.
So now once it is on, you will remove your bring your LDR from darkness to and expose it to light slowly and check how the brightness is decreasing or increasing or whatever is happening. That you have to infer in your experiment. Are you able to follow it?
Okay.
Okay.
In part 2, the again the other LED, yeah, this one.
Yes.
Over here as well, we have to make again 2 observations when LED is glowing and when LED turns off.
Yeah. Yeah, and you have to measure and record the voltage across the VC, that is VCE, this and this VCE, right?
Yeah.
And for both the on and off, note the voltage across LED. Across LED also you have to measure voltage, and the base current also. Here across RB you have to measure the voltage like that. Okay, and simultaneously we have to check for the open circuit value of the RP. Remove RP, remove RB at the time, and you will see when you connect the RB, there is a voltage drop, so you can't say how much voltage is there. Okay, see,
Yeah.
remove RB when the VGT is on and note the voltage at the variable terminal of the potentiometer, and simultaneously you take the voltage across this, and here it is grounded, so this 2 terminal you have to check the voltage when you remove the RB, correct?
Yeah.
So you will get to know that how much voltage is across RP is there across the variable end of the potentiometer is there, voltage drop is there due to Vs, correct?
Yeah.
Okay.
And we have to do both these parts in using both the devices, BJT
Yes,
as well
yes.
as MOS.
BJT as well as MOS.
Okay. So these observations
And
are
observations you have to which observation? This part
yeah,
3,
part
right?
2 and part 4 both
Yes, observations you have to show me in the
in a video.
video. Yeah, correct. And say that which one is better, which one has good power, less power consumption, which one will be better for different applications. That you have to infer also, because that is what, based on the experience with the BJT and MOS transistor driver circuits, draw conclusions regarding their suitability, efficiency, and practical considerations for driving LEDs and similar applications. Okay. Discuss any observed differences and advantages of one transistor type over the other.
Okay,
Okay.
fine.
Fine.
In part 1, we just have to plot the
Transfer
output
characteristic. Yeah.
output
Output
characteristic.
characteristic. Correct. Yes. ID
So,
versus I think VCE, right? ID
yeah,
versus VCE, IC
IC,
versus
IC versus VCE,
VCE, and
IC,
ID versus this one,
ID
VDS.
versus ID, VDS.
VDS, correct.
And
That's
the
it.
MOSFET part is not clear actually.
Yeah, I told, I think Venkat.
Yeah, Venkat.
Yes, ma'am, I'm
Yeah.
plotting
Have
the
you plotted?
Yeah, ma'am.
I-
1 second. 1 second.
I have plotted the BJT part. May I show the graph? Is it correct or not?
Yeah. Sure. Show me. Yeah, this should be the one. This is
Is it
VJT.
visible?
This is VJT.
Yeah.
It should be like this, no?
I don't know why, but I am getting this graph only.
No, it should. It is not. This way actually the MOSFET should come. Are you sure you are using VJT?
I'm trying with the BJT and I am getting this graph.
No, I don't think it is the correct one.
It should be straight, I know, but I don't know why.
What is the base resistance you are using?
1 kilo ohm.
There. What is the voltage, base voltage?
0.7.
No, not that. Supply from the potentiometer.
Supply to potentiometer is 2.5.
No, from the potentiometer, output of the potentiometer.
That I have not measured actually. I have measured only VB.
Okay.
Well, it looks correct only, by the way, because this is the early voltage thing that is coming here. The slope.
Which one? Wait, just a minute. So you are showing me for just a minute. This is for MOSFET or
This is for
IC?
BJT actually.
Okay. Just a minute. But it should be not like this, no?
I don't know
I
why,
see.
but I am getting this graph. I have plotted this 2 times and I'm getting the same actually.
Ma'am, almost similar graph I have also received.
And the sampling is also pretty well, so I don't think so there will be an issue.
Is this just for a single value of IB, like means the value across the potentiometer? Or are we varying voltage across potentiometer?
No, IB is not varying actually. Base current is same. Only collector current is varying.
DCC is varying, right?
Yes.
Yeah.
So how much voltage is across RP?
Voltage across?
Across a
Potentiometer.
potentiometer, Variable terminal?
2.5.
2.5? No, I think 1.5. No, not 1.5. Let's say you are connecting to the variable. So the total voltage you have given. No?
The total voltage is 2.5 to the potentiometer,
Correct.
and
And how much voltage across the variable end and the ground?
variable at ground.
Variable end of the potentiometer that you are varying, right? So that is
The output of potentiometer.
correct. Yes.
Actually, I have not calculated that one. I have not measured actually. I measured only base current and base voltage.
What is the base current?
Base current was about 0 point something. I don't remember actually. And base voltage is 0.7 that I'm sure about.
Base voltage is 0.7.
Yeah.
Okay. So then the VCE.
Yeah.
VBE. VBE is 0.7. Correct. It is right. And then base current is how much you are saying?
That I was not sure because it's about 0.4 or milliamperes. So,
Ma'am, VBE will not change because once it is
Yeah.
in
Yeah,
saturation, it
correct.
will remain in
VB
saturation.
VB will be
is
same,
actually
right?
constant
Correct.
only.
Yeah. VB
So
will change, not change.
what we need to vary is the IB, the current to the base.
Correct. Yes.
So I think we need to plot another such curve for a different value of IB.
IB will vary.
Yeah, of course. But that will
Uh,
vary only when we'll change voltage to potential. Yeah, or when we'll change the setting of
collector
potential.
voltage.
No, not collector voltage.
Collector voltage will be varying, no?
We will have to change,
Ma'am?
but to get a different curve, that's the objective.
Okay.
Yeah.
This is
Ma'am?
one curve for a particular value of IB. If we
Yes.
change IB, we'll get a different curve. I mean, the shape will be same, but at different level.
Okay.
Yeah. So, and that way, I believe we will be in a better position to compare if it is like early effect.
I will check that also. Right.
Yes, Akash Gupta, you wanted to say something.
Ma'am, I got this MOSFET graph. I plotted the MOSFET values.
Ma'am, so what I'm saying is, like, we can simply plug on ADLM kit and do this calculation straight away from that, right? The IDVD curve, the transfer characteristics.
Yes. From
So
there,
we can,
I have done that only.
yeah, we don't really need to like have a RC altogether. I mean, we can simply remove RC from the top. So the top VCC will be a channel A, and the channel B we can simply pour into the via a resistor, big resistor to the base of the BJT. So this is for BJT, and for MOSFET we can remove that resistor altogether.
I could not follow you. Can you just repeat? Sorry.
So
VCC,
I
what
said,
you will remove RC
yeah,
from
we'll
figure
remove,
1 you are saying, right?
yeah. So
Okay.
we'll put RC as 0.
Okay.
Then we can simply put a channel A on top of into the drain or the collector of the transistor. Okay. Now the ground is gone, the emitter or the source we have grounded. So now
Source is grounded now. Yeah.
source or emitter is grounded.
Emitter is grounded. Yes.
Okay. Now in the BJT case, we can take a big RB to limit the base current going in. We can take channel B and put it onto the other side of the resistor and then start supplying the IB. So here we will have the IB, we can control the voltage, and hence the IB going into the BJT. We can have a control of IB. So IB constant, then we can simply, this is channel B, okay. So we put some voltage on channel B, control IB, we set IC by this.
Yes.
And then we directly start varying VCE from channel A.
Correct. Okay. Yeah.
Because we don't have an RC. Then we can straight away have the curve. We don't really need to use the multimeter altogether.
So straight
So this
away
is
you can see the current across the this thing
yeah, because
from the
this
current.
channels because the channels can read current very accurately. Some, I mean, not accurate, but yeah, you can read currents through them. So this is what I was thinking to do in this.
Uh, or else can we do another thing, Akash? Like,
Yeah,
can
yeah.
we ramp signal and can we export the data and visualize it?
Can you go again? Export the
Uh,
data, what?
give a ramp signal, something,
Uh-huh.
and then
Okay.
export the data, and then we
Hmm.
can analyze it directly. Need not
Yeah.
even.
Yeah. You can do that.
I have used a triangular waveform and cut
Okay.
the specific portion of that.
See,
Actually,
for
with
you,
triangle.
the curve that you have shown before, just before, no. So
Yes,
that
ma'am.
is that that part it is going up little bit up, right?
Yes, ma'am.
So that is not an issue, I think.
Okay. Means the curve is correct.
Almost, yeah, because same thing for a different value of IB, you are changing. IB is
Uh,
staying constant, right?
yeah.
For that value, then you are just changing the VCC, right?
Yes.
And then you are getting right.
Yes,
So
ma'am.
practically, you will not be like not direct. It will not vary. It is not like that. Okay.
Okay, ma'am.
So MOSFET, have you done?
Actually, I'm trying for MOSFET, but I am not getting exact value of
Plotted
that.
the data which we have got before.
That's why I have asked for data sheet, and the data sheet is
I have shared. I
yeah,
think
but
Victoria
the
has shared.
data sheet was also not very accurate for this. So I'm not able to.
Well, I would like to say something on this
Yeah.
MOSFET thing.
Yeah.
Yeah.
So, I have used these IRF 640 or 540 series MOSFETs earlier in some of my projects. So these
Okay.
are actually power MOSFETs. So be a little bit careful with them. Their VG, I mean VGS TH, the threshold voltage is not really accurate, and they have a very high gate capacitance.
Correct.
Very
I
high
agree.
gate capacitance. So be very careful when you put like do you have you guys like put in some signal into it, or what have you done?
Just varying the voltages.
No. I'm saying, have you put some time varying signal like a triangular wave or something?
Yeah, triangular waveform I have used.
So try doing it using constants.
Yeah.
I
Yeah, I
have
It
have
is.
tried that also.
constants only.
You have tried that?
Yeah.
So only give like constant voltages as given in the experiment. Okay, assignment. Okay. So
This is the graph which I got
yeah, just
with the values before we have recorded.
I think it
Okay.
is this part. I'm not sure.
For MOSFET,
Yeah.
This is VDS value and ID value.
What is on the x-axis?
It is
VDS.
VDS.
I
VDS
think you
is
should increase the resolution of VDS, I think.
correct.
Okay.
You should have to
Maybe
increase take some more points,
Yeah,
more
yeah.
like
points.
0
Yeah,
to 1.
from this
0
like
to 1.
0 to I think
0 to 1 or 2,
zero
take
point
more points.
3623, right? VDS
Yeah.
value. You can have some more points and check how it is changing.
Okay, ma'am. I'll check it. At some abstract level, this is correct, right?
Yeah, it should be like that only.
Okay.
Yeah, but it's take some more
Yeah,
points
I'll take it and
in the lower region. Then that's I think that will give you an answer.
yeah, thank you.
Excuse me, ma'am, but
Yes, ma'am.
when I did the experiment for the MOSFET, I got the drain current to in milliamperes.
Yeah. Drain
Uh,
current in milliamp is how much current you're getting?
uh, the maximum which I got was around 0.9 milliamperes. That is not an issue, right?
No, I think this will be the range. I think that is fine.
Okay, ma'am.
Excuse
And
me,
ma'am,
ma'am.
Yeah. Yes.
ma'am, the graph for the BJT and the MOSFET are almost same, very slight difference. Is that the case, or the graph should be different?
No, see, whatever the graph should come approximate, that should be there. But what is your question actually? What is the difference means? I didn't get it.
No, I have plotted the graph between the current and voltages, the collector emitter voltage versus the IC current.
Mm-hmm.
Similarly, I have done for the MOSFET also.
Okay.
But the rise in current with the increase in voltage is almost the same. But shouldn't it be higher for the MOSFET?
That will find out. What should
Ma'am,
be the yes?
ma'am, I have a small thing to ask. Ma'am, in my multimeter, currently the current measuring part is not working. So can I take help of the these simulation softwares like Multisim to measure the current?
See, you can measure. You don't need no need to directly measure the current. You can maybe you have to current the ID, for example, okay, or IC,
Oh,
for
okay, ma'am.
example. You can
Yes.
take the voltage across RC, right?
Okay.
And then
Okay.
you divide it by
That way.
that is the
Okay.
simplest way.
And in the videos, shooting the videos, can I use the simulation softwares like
Simulations.
along with the circuits?
Yeah, you can use the which simulation software are you saying?
Ma'am, currently I am going with LT Spice and Multisim.
Okay, so simulation software, but you have to do the experiment, right?
Yes, ma'am, I have designed the complete circuit on the simulation software, and
Okay.
then after confirming the values, I am
Okay.
building the circuit.
Okay, maybe you can show if you have done, you can very well show it, no problem.
Okay, ma'am. Thank you, ma'am.
Ma'am, but one more small thing. With this particular MOSFET, the same model, I am getting certain threshold voltage. One of my friend is getting some other threshold voltage.
Yeah, it might vary.
Then in that case, we can't use the simulator, right?
In that case, you can't use the
Simulator.
Simulator will get you get the voltage approximately ideally, right?
See, this LT Spice simulations softwares they will give the ideal voltage or it's ideally what should come. But
Yes, ma'am.
In experiment, it will always be different. Okay, so don't compare that with that. Only what you can confirm is that whether the graph it is coming in the same way or not. Plot,
Okay, ma'am.
that plot variation is in the same is showing the same trend or not. Okay, not exact values will not replicate in the experiment. Right?
Yes, ma'am.
Yeah. Okay. So any more doubts?
Yes, ma'am. In the BJT transfer characteristic, the value I'm getting varies by a lot, ma'am.
Which one? Transfer characteristic? What value you are saying?
Yes, ma'am. The BJT transfer characteristic, building the circuit as was instructed, I'm, I'm getting between 7 to 15, like that much variance I'm getting.
7 to 15 ID value? What value?
Yes, ma'am, IC value.
IC value? See, are you getting the graph proper? Same
I'm getting
trend
a
of the
straight
graph?
line, ma'am.
No, then it is wrong.
Yes,
So at some point there will be saturation, right?
yes, ma'am. I'm not sure whether it is
You are doing the same connection. You are doing wrong or not? That is what?
no, ma'am. I'm doing the connection as was given in the document, but I'm not sure if I'm using too big of a increment or something like that. Like I'm using 0.5 volts.
From 0 to 5 volt.
Yes, ma'am.
So 0.5 you are increasing, right?
Yes, ma'am.
Yeah, that is you can if it is not there, then you can try 0.25 also. See what is it. Okay.
Ma'am, that is
But
that is
will
not
not
the
change.
issue, ma'am. Yes,
That will not change the graph trend, right? You are doing
no,
anyway.
ma'am. The issue is that for the same value of VCC for everything keeping the same, the value of current is changing from, like I'm seeing it right now, it's from going from 13 point something to
Okay,
like
it is variation is very much that it is flickering.
yes, ma'am. Like I'll just show what I'm seeing. Just 1 second, ma'am.
Yeah, sure.
So this
Just
one,
a
ma'am.
minute, just a minute.
Is it visible now?
Yeah, you are sharing the screen now.
No, ma'am. I'm using the video.
Just yeah. Yes.
Yes, ma'am. So this is what I'm getting, ma'am.
Changing a lot. It
Yes,
is
ma'am.
in what?
And this is the circuit.
Yeah, what are you measuring in the multimeter? What you have put
It's in milliamps, ma'am.
in?
Ma'am,
Yeah.
yes, ma'am, we should turn off the repeated sweep.
Yeah, that is one thing. Yes, correct. I forgot. Have you turned off the repeated sweep?
The repeated sweep, ma'am. Uh, yes, ma'am. I turned it off, and now it's
It is constant.
yes, ma'am.
Yeah, yeah. I think that is the issue. Yeah.
Okay, ma'am. Thank you.
Yeah. Thank you. Thank you. Any other?
Ma'am,
Yes.
so ma'am, as per the document, we should keep the IB or IG constant and just change the
This is
VC. Yeah.
yes.
So we will get only one curve, right, ma'am?
Yeah, for yeah, we will get only one curve. Then if you change the IB value, then another curve like that, no?
Yes, ma'am. But
For different
we are
IB
supposed
value,
to do only for one IB.
yeah, yeah, you can suppose you can do only for one IB.
Yes, ma'am. And the general trend for both BGT and MOSFET is same, right?
General?
The trend of the graph
Yeah.
is same, right? So it should look similar.
Yes, but you check by yourself what you are. Have you gone through the theory properly? But there will be some changes, like which one will have more power consumption, and like why RB is not connected. If we remove the RB value, if we can remove the RB from while connecting the gate in MOSFET, why so? So those things will be different. Okay.
Yes, ma'am. Yeah.
Any other doubt?
And can you please repeat how to get VGS?
VGS. Just 1 second. I'll just...
Yeah.
So you wanted to know how to get VGS?
How to get VGS of MOSFET?
Gate source voltage of VGS.
Right. Right.
So I told you, I think previously.
And that's actually I'm not able to understand. That's why I'm asked.
Okay. So you will fix the voltage. Maybe 2.5 or 5 volt. What is it? Whatever it is. Now, RP value, the variable end you can change, right?
Yes.
Your variable end you have connected to RP to your to your MOSFET.
Yeah.
Correct.
Yeah.
Now VCC you can put it at 5 volt, maybe.
Okay.
So in the first run itself, right?
Yeah.
You keep it at 5 volt, and RC it is connected through RC it is connected. Correct. Now you change the value, change the RP value. Okay. Potentiometer, you vary the potentiometer value.
Okay.
Okay, so maybe make it a little high. Let's say maybe 3.4 or 3. If you're connecting 5 volt, you get 3.4 or 3, like that. Okay.
Okay.
Like so for that, some good amount of current is passing through across RC. So measure the voltage across RC.
Okay.
So you'll get a voltage across RC, right? From there, you will that voltage divided by RC will give you the ID, right?
Right.
Now you check that for now you change the VCC value from 5 volt, you decrease down to 4.5, 4, 3.5, like that. Okay.
Okay.
And check the values of ID.
Okay.
It will be almost constant, right?
Right. Right.
Then like you decrease it, and at some point it will reduce, right?
Yes.
That plot you have to show.
Okay. Thank you.
Yeah. So all the doubts are clear. Shall we wrap up? Any more doubts? Victoria, shall I wrap up? If you don't have any more doubt, you can leave the meeting.
Thank you, ma'am. Thank you for your time.
Yes, ma'am. Thank you, ma'am.
Thank you, ma'am.
Thank you, ma'am.
Thank you.
Thank you, ma'am.